everybody, this is my third try. Now we are jumping into the MDA 102 course, and we shall deal with the infinitesimal approach to the same thing as we are doing in the other one. So our first task will be to create a big enough space of functions to serve our purposes and being able to build models. So therefore we are talking about establishing the zoo here. And actually the only functions we really can work with are the polynomials, because that's what they are, right? So you see, you simply have an expression where you can multiply and add. And so this kind of expression, polynomials, work with all scalars, and such a formula gives you a function which eats one of the scalars, called x in my case, and you have got a lot of parameters, a0 up to an, and can be as big as you can imagine, but finite, and you can compute. So that's what the computers can do, and on top of that we can divide polynomials, and that's about it, right? So of course, whenever you have a space of functions which has values in scalars, in our case our scalars will be in this part of our mathematics more or less always only the fields, rationals, reals, and complex numbers. We are not interested in more complicated analysis now. And whenever you have functions valued, defined on any set and valued in such a field, then of course you can do the operations pointwise, and you again get behavior which is very similar to scalars, except not all the properties hold true, right? So for example, if you have polynomials, then of course you can multiply them as described here, you can add them as described here, and all the properties of the scalars will hold true, except that the functions are having roots, so they are sometimes zeros, or they might be. So the polynomials, I mean, and therefore you can't divide, so it won't be a field, it will be just a ring, right? But still, many of the behaviors are there. So that's the polynomials, and we can always view polynomials as a function, but we can also view it as an algebraic gadget, right? And in the course of our studies, we shall do both now. They are functions for us, and there is the well-known Euclidean division of polynomials, where you can divide a polynomial by a polynomial with a smaller or equal degree. That's the highest power appearing in the polynomial with a non-zero coefficient, and there is a remainder, and the remainder is either 0 or it has got smaller degrees. So that's the main tool we are using with polynomials. You can see how it works, and now there is a clear question and task to deal with. So say we have got some data, we want to work with them, and we know the data in some given number of points, say 4 for us, and we know the values, so let's say these, so that will be the values. And now I'm questioning whether I can write a polynomial which would just go through these data, so it would just then look something like this. Right, so that could be a polynomial of mine. And of course you see that if the values would be all zeros, then what we get is a possibility to write a polynomial this way. So x is the variable, and x0, x1 up to xn are the points we request the polynomial to have the 0 value, right? And of course you see that this polynomial would be of order n plus 1, because we have got n plus 1 points. In our case it would be 4. Yes, it would be 4, so n is 3 in our case, and what you would get is quite a wiggly polynomial. But there is another polynomial, the 0 polynomial, just constant 0 everywhere, which would fulfill the same thing, and this will be of order less than 4, and at the same time, well, it won't have order because it's 0, but who cares? So the real task for polynomial interpolation is to find a polynomial which is of order at most n, if we have got n plus 1 points. And that's because a polynomial of order n has got n plus 1 coefficients, right? So it's not such a big surprise if you write down the conditions. So you see that the values of the polynomial index 0 up to xn are prescribed to be y0, yn. And so if I view a0 through an as unknown parameters, then this is a system of linear equations. And now we can question whether we can solve it, whether it has got always a solution. That's what we shall do in next weeks. But in our case, it's much easier. The life is much easier because we can write down the so-called Lagrange polynomials. And the Lagrange polynomials have got the feature that they are, so the ith one has got the value 1 in the ith point and 0 in all the others. So and it's quite easy to write down such a polynomial. Imagine we have got only say 2 points, right? So if we have only a and b, then we simply write L 0 of x would be equal, and now we simply say that it will be x minus b divided a minus b plus x minus a divided b minus a, right? And you see that this very polynomial, if I have only 2 points in which I do it, so it will have, so for x equals a, this will be 1 and this will be 0. So this is 1, this is 0. For x equals b, this is 0 and this is 1. That's exactly what we want from the Lagrange polynomials. And then we can write down our polynomial explicitly this way. So you see, it's a very easy task, and the polynomials can be interpolated this way. The problem is that the polynomial interpolation, as we shall see, I will come then to some example. They are very unstable and bad in approximation of the original function in the end of the interval. So horrible outside and quite bad in close to the end, right? And we might think that actually they tend to run towards infinity or minus infinity very fast. So, and we might think that it's because we have not controlled the behavior, right? So you see that infinitesimally the polynomial is growing this way here and this way here, this way here, and maybe we know about the data what kind of infinitesimal behavior we would like to see. And this is not that difficult to see because we can imagine what we want to do, right? So we want to understand how the behavior of the function is changing if we change the argument only infinitesimally. So if our function is something like this, right? So we can imagine that at this point we simply look at the function and we looked how much different it's here, and we want to see what would be the right approximate of that point. Here it would be just this way, right? And that's what we call derivative. And for polynomials it's very easy, because for polynomials you can easily see, here it is, you can simply easily expect that the change should be of this kind. So you look at the difference of the two very nearby points, and you divide by the change of by the magnitude of the change of your variable. And with polynomials, you see, first of all, this will behave additively. So you can deal only with one of the terms in the polynomial. It will be constant times this guy, right? So if you change anything by constant, then the constant will be the same here and the same here, and therefore we may see that the constant will be just put outside of the thing. So if you just understand merely this easy thing, then we are doing this way. And you see that this is just a binomial expansion, right? So it's not so difficult to go through. Actually, we have learned what the k over L means. It's the combination number. It's a number of how many times I can pick up L of the x's in the k bracket to form the product, and the rest will be the del's. So that will be always this way, right? But what you see is that if we make delta x small, then the higher the power, the smaller the delta x will be. So we can neglect actually all, if we subtract the value at x, so that will be the first one. So it will be just this one, and then what's remaining is just the first one, which has got only the delta x to power 1, right? And that will be k times x to k minus 1, and that's the derivative of the polynomial. So you see that actually that's a very straightforward thing, and you see that the derivative of the polynomial makes sense, and by the very construction it will give you the slope, so how fast the polynomial function grows. And now this is the way how to come to what's called the Hermite interpolation, where we are supposed to prescribe not only the values but also the derivatives. So you can imagine it the easiest way. If you have 2 points, x0, x1, you've got two values, so it's y0 and say y1 will be here, and you also have the derivative, so this will be the slope of the function here, and this will be the slope of the function here. So you see we have got 4 conditions for the 2 points and 2 first derivatives, so we should look for third order polynomial. And that's exactly the case, right? So if we prescribe the 4 things, you go for the first or third order. I will just skip the technicalities. It's quite annoying and tedious, so I suggest you won't also spend much time. Simply, the story is that whatever we did with the Lagrange polynomials and constructing the interpolation, we can just repeat and do the same for the Hermite one. It's just technically more complicated, and you can go to as many derivatives as you wish, right? So the most strange thing would be you start with 1 point x0 only and give k derivatives and the value, right? And then you know that you will just prescribe exactly one polynomial, which will be of order how much? So it's 0, yeah, so there will be k plus 1 condition, so it will be k's order polynomial. Right, but the quite fascinating idea, typical engineering in a mathematical way, right? So mathematics, the mathematicians simply, so usually think that the engineers are not doing right things because they are simplifying things too much. But actually the good engineers are just doing the real mathematics because they are trying to simplify as much as possible to still keep things going. And that's what the mathematical approach should do. And the splines are absolutely ingenious because the people just came up with thinking out of the box and thought, well, that's a really nasty thing, because how the hell should I know from the data what the derivatives are, right? And so how could I do the same thing? So if I have many of the points, say x0, x1, and so on, so there will be more coming. Then what I can wish is that I would seek for third order polynomials, as here, for the individual intervals. But instead of requesting explicit values of the derivatives of the border, which would be then shared for the neighbor, I just wish that two derivatives, two, not only one, are shared. So I request that the derivative for the polynomial coming from the left is the same as the one starting in the right? And then in total, I will get the same number of conditions, except on the very end, right? At the very end, I'm lacking one. So there the people add some condition. Don't worry about it. And that's what the people call spline. So in the British English or real old English, spline was meant as this ruler for the engineers, where you can elastically make the shape, right? And that's exactly what the splines do. So I will not go into details how to compute spline, that's more complicated, but it's possible, of course, in our software, for example, in Sage. And so let's go to the example I promised. So here is a simple code as usual. I will again get it into the mouse. I'll go to the Sage cell. I throw it in. Let's evaluate it. So first I tell what it is, right? So you see roughly speaking, what we do is we simply take a function we want to interpolate, right? So it's just some function. You will see it on picture. Then I create the points for the interpolation. So it's always x and yx, and I run with x in the range from -3 to 3. And here, just telling what the next one is with the dots for the Sage. He's so smart. He just understands that I want to have the distances between the points the same all the time. So that's saying that I'm jumping by 0.2. And then I let him show as a picture how the points look. And I also add the spline there, right? So that's the spline function just given by Sage. So that's the spline going through the data in V, and I go from -3.1 to 3, right? I don't know what I put 0.1 there, but it doesn't matter, right? And then I create another set of points where I simply hit the function value. So this is something like real measured data, right? And measured data are always hit with some error. So I create real random numbers in the range from -1/10 to +1/10, and again I do the same as before, right? So that's the V, and I show what the splines would do with this slightly deformed data, right, by the errors, and we shall see that it's very stable. And then what I do is I create a polynomial ring, and I just write down the Lagrange polynomial for the data V, and I do the same for the W, right? And I show how they look. So that's what I do. And if you evaluate, you see the first picture, it's what we get for the spline. So you see this is the function x squared times sine. So at 0 it's just pushed to 0 much more, and you see that the spline is doing absolutely perfect job, right? So there is no problem at all. If I make the data more wiggly, then of course the spline gets also more wiggly there where the data were sort of close to 0. So here you see, so you see how much the random thing was changing. And here let's have a look at the polynomials, right? So as long as the function was sort of reasonably behaved, so the polynomial interpolation is not that bad. So let us do that. So if I instead say do it this way, 3, 3, 3, 3, 3, 3, 3. See that with the wiggled one, I am just I'm just already cutting off the things, and I will do the same here. Y min equals minus 3, y max equals 3. And if we now evaluate, of course we get, yeah, sorry, so that's not a problem. Yeah, well, I mean, with the spline it is, so I should remove this because he has got problem. The spline doesn't exist outside of the so I leave it minus 3, 3. The polynomial is a polynomial, so it exists everywhere. The spline exists only in the interval of ours, right? So let's do it this way. Right, so you see the splines are doing quite a good job. The polynomials are absolutely horrible because they just tend to run away, right? They run away to infinity here, to minus infinity here. And although inside of the interval it wasn't that bad, outside of the interval it was horrible. But look what happens with the polynomials when I randomly change the data a little bit, right? And then immediately, because it's not that nice already, it starts to wiggle from minus much to plus much already inside of the interval. So this is why I had to cut it off, but by plus minus 3, right? So this is the result, and I think that's also the end of my presentation for this week. So thanks a lot.